Hello there, dreamers, and welcome to the Sleepy Science Channel. I'm absolutely thrilled you've found your way here because tonight we're embarking on a tranquil journey into the heart of physics's most profound enigmas. We'll be pondering those quiet, lingering questions that dance on the periphery of our knowledge, gently nudging the very fabric of what we think we understand. Right now, as you settle in, the night sky blazes with an uncountable number of stars, swirling galaxies, and wonders yet undreamed of. Their light, ancient and tireless, has traveled for millions, even billions of years, crossing impossible distances just to reach you in this very moment, in this quiet space. Isn't that humbling? Despite all our technological advancements, our intricate theories, and meticulous observations, we still remain profoundly ignorant about the composition of the vast majority of the universe. We've painstakingly mapped the galaxies, charted their graceful spirals and chaotic collisions. We've measured the age of the cosmos with ever-increasing precision. We've even managed to trace the faint echo of the Big Bang, that cataclysmic birth of everything. But beyond all that familiar territory, something else lurks, something immense, invisible, powerfully influential, and for the most part, utterly unknown. We're talking about dark matter and dark energy, those mysterious forces and substances that sculpt the cosmos on the grandest scales. They bend galaxies into graceful arcs, accelerate the universe's expansion with inexorable force, and are actively rewriting the very boundaries of what we thought physics could explain. We see their effects. We know with increasing certainty that they're there, but we haven't the faintest idea what they are, and that, my friends, is where our adventure begins. All across the observable universe, galaxies are spinning. Vast, majestic wheels composed of countless stars and swirling clouds of gas, all whirling through the endless void of space. But back when astrophysicists first began carefully measuring the speed at which these galaxies rotated, they stumbled upon a significant anomaly. Something simply didn't add up. The stars at the outermost edges of these galaxies were moving far, far too quickly. According to our current understanding of gravity, based solely on the visible matter, the stars themselves, the planets orbiting them, the diffuse gas clouds scattered throughout, those outer stars should have long ago been flung off into the intergalactic abyss. They simply didn't have enough gravitational glue holding them in place. Instead, they stubbornly remained in orbit, behaving as if held captive by some unseen, invisible force. That force, it turns out, is what we believe to be dark matter. We call it dark, not because it's inherently sinister or malevolent, but simply because it doesn't interact with light in any discernible way. It doesn't emit it, doesn't absorb it, and doesn't reflect it. It's effectively invisible to our eyes, to our most powerful telescopes, and to every known form of electromagnetic detection. And yet we know it's there. Not by seeing it directly, but by observing its profound influence on the universe around it. It tugs on entire galaxies, subtly warping their shapes. It bends the path of light as it travels around massive galaxy clusters, creating eerie distortions in the images of distant objects. And it sculpts the very large-scale structure of the universe, shaping the cosmic web that connects everything. In fact, dark matter outweighs all the normal matter we can see by a staggering factor of 5. In a very real sense, dark matter dominates the cosmos. We just have absolutely no idea what it is. The story, as so often happens in science, begins with an inquisitive mind. In this case, it was the 1930s, and the mind belonged to a somewhat eccentric Swiss astronomer named Fritz Zwicky. Meticulously studying the Coma Cluster, a gravitationally bound group of thousands of galaxies, Zwicky noticed something odd. The galaxies within the cluster were moving with such incredible speeds that, according to his calculations, they should have long ago flown apart, scattering into the vastness of intergalactic space. But they hadn't. They were stubbornly sticking together. Zwicky, ever the contrarian, proposed a radical solution: that some unseen mass, which he rather poetically dubbed dark matter, must be providing the additional gravitational force necessary to hold the cluster together. His ideas, considered quite outlandish at the time, were largely dismissed by the scientific community and languished in relative obscurity for decades. But then in the 1970s, a new generation of astronomers, led by the brilliant Vera Rubin and her colleague Kent Ford, took up the torch. They meticulously observed the rotation curves of individual galaxies, carefully measuring the speeds of stars at different distances from the galactic center. And what they found confirms Zwicky's earlier suspicions. They observed the same strange, inexplicable pattern. Outer stars were moving far too fast. The gravitational pull of the visible matter alone simply couldn't account for their velocities. It was as if something else, something invisible, was providing the necessary gravitational boost. Since Rubin and Ford's groundbreaking work, galaxy after galaxy has revealed the same telltale signature, flat rotation curves that stubbornly refuse to decrease with distance, as Newtonian physics would confidently predict. It's as if each galaxy is embedded within a vast invisible halo, a cocoon of unseen mass that we cannot directly observe but must nonetheless account for. Even when galaxies collide in spectacular cosmic crashes, the dark matter behaves differently than the normal matter, the gas and stars that make up the visible components. It passes right through, completely undisturbed, like a ghostly apparition. The Bullet Cluster, a pair of merging galaxy clusters, provides one of the most visually striking pieces of evidence for this phenomenon. By employing a technique called gravitational lensing, astronomers were able to map the distribution of mass within the cluster with unprecedented precision, and what they found was remarkable. The region of highest mass concentration didn't coincide with the glowing clouds of visible matter. Instead, it was offset, aligned with the region where the dark matter was believed to reside. Gravitational lensing, the bending of light by massive objects, has become one of our most powerful tools for indirectly detecting and mapping the distribution of dark matter. Light from a distant galaxy passes through a massive galaxy cluster on its journey to Earth. The cluster acts like a lens, warping and distorting the image of the background galaxy. By carefully analyzing these subtle distortions, astronomers can reconstruct the mass distribution in the foreground cluster, even if they can't directly see the dark matter itself. And again, these gravitational lensing maps reveal that there's far more mass present than can be accounted for by the visible stars and gas alone. And yet, despite this overwhelming body of indirect evidence, dark matter continues to stubbornly evade direct detection. We can describe its effects with exquisite precision. We can calculate how much of it there must be in any given region of space. But the fundamental particles that make up dark matter, the very stuff of which it's composed, remain shrouded in mystery. These particles, whatever they may be, do not appear to interact with ordinary matter through any of the known forces, except for gravity, and even that interaction seems remarkably weak. So what could it be? Over the past few decades, physicists have proposed a bewildering array of candidate particles to explain the enigma of dark matter. One of the earliest and most thoroughly studied possibilities is the WIMP, or weakly interacting massive particle. WIMPs are hypothetical particles that interact with ordinary matter via the weak nuclear force but not the electromagnetic force, which is why they're invisible to light. Their predicted mass and other properties arise naturally in many extensions of the standard model of particle physics, including theories like supersymmetry. For years, WIMPs were considered the leading contender, the most promising solution to the dark matter puzzle. Entire underground laboratories were built at enormous expense specifically to try and catch these elusive particles. Massive ultra-sensitive detectors were buried deep underground, shielded from cosmic rays and other sources of background noise, patiently waiting for the infinitesimally rare collision between a WIMP and an atomic nucleus. But none came. As experiment after experiment returned null results, the focus of attention began to shift to other, more exotic candidates. One such candidate is the axion, a lightweight, ghostly particle first proposed to solve a different problem in quantum chromodynamics, the theory of the strong force that binds quarks together inside protons and neutrons. Axions are incredibly light, far lighter than electrons, but they could exist in such vast quantities that they collectively add up to a significant source of mass. Specialized detectors are now being designed and built to tune into the narrow range of frequencies that axions might produce as they convert into photons in the presence of a strong magnetic field. Other ideas go even further afield. Sterile neutrinos, hidden sector particles that interact with ordinary matter only through gravity, even primordial black holes formed in the earliest moments of the universe. Some researchers have even suggested that dark matter might not be a particle at all, but rather a modification of our understanding of gravity itself, an approach known as modified Newtonian dynamics, or MOND. And yet, despite all these efforts, none of these theoretical ideas have yet definitively solved the riddle. What dark matter is ultimately made of remains a mystery, but what dark matter does, how it shapes the universe on the grandest scales, is becoming increasingly well understood. In fact, without dark matter, the cosmos as we know it simply couldn't exist. In the very early universe, shortly after the Big Bang, ordinary matter was far too hot and energetic to collapse and form structures. It interacted strongly with light, which kept it from clumping together under the influence of gravity. But dark matter, being largely unaffected by radiation, could begin to form dense regions even in those earliest moments of cosmic time. These regions of higher density then became gravitational wells, attracting ordinary matter and serving as the seeds around which galaxies and larger structures would eventually grow. This way, dark matter served as a kind of scaffolding, providing the initial framework upon which the visible universe was built. Tiny fluctuations in the density of dark matter, amplified by gravity over billions of years, provided the seeds around which galaxies and galaxy clusters could coalesce. Sophisticated computer simulations of cosmic evolution vividly illustrate this process. When dark matter is included in the simulations, the resulting web of large-scale structure, with its intricate filamentary networks of galaxies and vast cosmic voids, closely matches what we observe in the real universe. Without dark matter, the simulated universe looks nothing like the one we inhabit. There would be no galaxies, no galaxy clusters, no stars, and very likely no us. It's not just about the formation of cosmic structures either. Dark matter continues to play an active role in holding galaxies together, even today. Its presence helps to explain the stability of spiral galaxies, the shapes of galaxy clusters, and the subtle patterns we observe in the cosmic microwave background radiation. These fingerprints, subtle ripples in the afterglow of the Big Bang, match the predictions of a universe in which dark matter outweighs ordinary matter by a factor of 5 to 1. It's not just a convenient patch for missing mass, it's woven into the very blueprint of cosmic evolution. And yet we still haven't found it. Not directly, not unmistakably. The scaffolding is there holding up the cosmos, but the beams themselves remain invisible. So why can't we find it? Despite decades of intense effort by physicists and astronomers around the world, not a single confirmed dark matter particle has ever been observed in a laboratory. The problem boils down to one of interaction. Ordinary matter reveals its presence in countless ways, through electric charge, the emission and absorption of light, the transfer of heat, the effects of friction. But dark matter seems to interact with ordinary matter only through gravity and perhaps the weak nuclear force, and even that interaction is incredibly weak. That makes it extraordinarily difficult to detect. Most particles, from neutrinos to cosmic rays, pass through our bodies by the trillions every second, completely unnoticed. Dark matter does the same, but without leaving even the faintest trace. Experiments designed to detect WIMPs, for example, rely on the incredibly rare chance that a dark matter particle might occasionally strike an atomic nucleus within the detector, transferring a tiny amount of energy. These detectors are often buried deep underground, in old mines or mountain caverns, meticulously shielded by tons of rock and other materials to block out cosmic rays and other sources of background noise. But even with extreme sensitivity and years of continuous observation, the results have remained frustratingly empty. Other methods, such as searching for dark matter annihilation signals in space using gamma-ray telescopes, or attempting to produce dark matter particles in high-energy particle accelerators, like the Large Hadron Collider, LHC, at CERN, have also failed to yield any conclusive evidence. It's entirely possible that we've been looking in the wrong place or for the wrong thing. Part of the difficulty may lie in our initial assumptions. Many of the early searches were guided by elegant theoretical frameworks like supersymmetry, which predicted specific kinds of dark matter particles with particular mass ranges and interaction strengths. As those possibilities are systematically ruled out by experiment after experiment, the parameter space widens. Dark matter could be lighter, heavier, colder, more diffuse, or something stranger altogether. It may not even exist in the form of particles at all. It may behave like a field, permeating all of space. It may interact with itself in ways we haven't even imagined. Or, more radically, perhaps our understanding of gravity breaks down on the largest scales, requiring us to fundamentally rethink our theories of how gravity works. Each path leads deeper into uncharted territory, into realms of physics that are still largely unknown. And that's precisely what makes the dark matter mysteries so profound. This isn't just a case of a missing piece in the puzzle. It's a sign that our entire picture of matter, of what the universe is ultimately made of, may be fundamentally incomplete. The standard model of particle physics, while incredibly successful in explaining a vast range of phenomena, simply doesn't include dark matter. Whatever dark matter is, it lies outside our current theoretical framework, which means that it isn't just a problem for cosmology or astrophysics. It's a doorway to new physics, a tantalizing glimpse into a reality beyond our current understanding. If we can finally unlock the secrets of dark matter, we may well open the door to entire realms of particles and forces that we've never even dreamed of. Our current view of matter is based on a relatively small number of familiar building blocks: protons, neutrons, electrons, and their interactions through the four known fundamental forces. But nature may be far more diverse and complex than we currently appreciate. Dark matter could be just the tip of an unseen sector of physics, a shadow world with its own unique particles, its own symmetries, and its own distinct dynamics. This possibility fundamentally reshapes how we think about the cosmos. The matter we see, the stars, the gas, the planets, even ourselves, might be just a thin glaze on the surface of a much deeper, more mysterious reality, a kind of luminous icing floating on a vast, dark ocean. We've spent centuries meticulously studying the visible universe, carefully cataloging its contents and unraveling its laws. But if dark matter truly dominates the cosmos, as all the evidence suggests, then the vast majority of the universe is still invisible to us, not just in appearance, but in essence. And that realization is profoundly humbling. It suggests that what we call normal matter may not be normal at all, just familiar. In recent years, the search for dark matter has grown increasingly creative and more urgent. New generations of detectors are being developed, pushing the boundaries of sensitivity to unprecedented levels. These cutting-edge experiments are probing weaker interactions in lower mass ranges than ever before. Some experiments are now specifically targeting ultralight dark matter candidates using techniques like resonant cavities, superconducting circuits, or even vibrating crystals to detect the faintest of interactions. Others are looking to the skies, searching for indirect evidence of dark matter annihilation or decay. The Fermi Gamma Ray Space Telescope, for example, is scanning the galactic center for telltale gamma ray signals, while gravitational wave detectors are exploring the possibility that dark matter might consist of a population of tiny primordial black holes formed in the very early universe. Still others are turning to quantum technologies, using cold atoms, interferometers, or nanoscale sensors to detect the faintest of tugs, the slightest deviations in the gravitational field that might be caused by the passage of a dark matter particle. But with every new approach comes more complexity, more challenges, and more questions. What if dark matter isn't just one thing, but a mixture of different components? Could it consist of multiple types of particles, in much the same way that ordinary matter is made up of protons, neutrons, and electrons? Might dark matter interact with itself, forming invisible structures or dissipating energy in ways that we haven't yet been able to detect? And perhaps most troubling of all, what if dark matter doesn't exist at all? What if the evidence we're seeing is pointing not to missing mass, but to a fundamental misunderstanding of gravity? Modified gravity theories, like MOND, modified Newtonian dynamics, or emergent gravity, offer alternative explanations for the observed phenomena, although they remain controversial and incomplete. The truth is, we simply don't yet know, and that uncertainty, while often frustrating, is also what makes this search so exciting, so intellectually stimulating. Because to solve the dark matter mystery is to confront the very boundaries of human knowledge. We're no longer just weighing galaxies or mapping halos. We're testing the limits of our theories, our tools, and our understanding of what the universe is ultimately made of. And in doing so, we're reminded that the cosmos still holds secrets, vast, invisible, and patiently waiting to be discovered. It might be hard to believe, but the story gets even stranger. In the late 1990s, two independent teams of astronomers were engaged in a rather ambitious project, studying distant supernovae, those brilliant stellar explosions that serve as cosmic mileposts, allowing us to measure vast distances across the universe. They were so the soup something, but even but like the it was, but now it encom these all depending, but no, it doesn't. This in the early, but as since then, eventually and yet is it even to study these because that's how the cause embed when dark other taken to the leading theoretical explanation, the vacuum energy of empty space turns out to be deeply problematic. Quantum field theory tells us that even a perfect vacuum, devoid of all matter and radiation, isn't truly empty. Instead, it seethes with temporary particle-antiparticle pairs popping in and out of existence in fleeting moments. These quantum fluctuations give rise to a non-zero energy density, and in theory, this vacuum energy should behave exactly like the cosmological constant. But when physicists try to calculate how much energy this vacuum should contain, the numbers go haywire. The theoretical prediction is off by a staggering factor, somewhere between 10 to the power of 120 and 10 to the power of 38 times larger than what we actually observe. This enormous discrepancy is often called the worst theoretical prediction in physics. Why is the vacuum energy so small? Why is it not zero, as one might expect? And why is it roughly the same order of magnitude as the matter density of the universe right now? These fundamental questions have no satisfying answers. Some physicists suspect that an unknown symmetry cancels out most of the vacuum energy, leaving only a tiny residue. Others invoke the anthropic principle, the idea that we observe this particular value of the vacuum energy because only universes with similar values can support the emergence of life. But these are not fully predictive explanations. They are more like placeholders for deeper insights that are yet to come. In response to this theoretical crisis, a plethora of alternative theories have emerged. Quintessence models posit a dynamic field, similar in spirit to the Higgs field, that slowly evolves over time. Unlike a constant, its influence can grow or fade depending on the properties of the field. This opens the door to a wider range of possible cosmic fates, but also makes the physics far more difficult to constrain. The space of possibilities becomes enormous, and without firm observational handles, many of these models remain highly speculative. Still, some of them do leave potentially observable signatures, such as subtle changes in the equation of state of dark energy, the relationship between its pressure and density, or variations in its density with redshift, a measure of how much the light from distant objects has been stretched by the expansion of the universe. Future observational surveys hope to test these predictions and either confirm or refute the quintessence hypothesis. One of the most striking consequences of dark energy is its effect on the geometry of space-time itself. In Einstein's theory of general relativity, the distribution of energy and matter determines the curvature of space. In a universe dominated by matter, the curvature depends on the total density. If the density is high, space curves inward, forming a closed universe that is finite in extent. If the density is low, space curves outward, forming an open universe that extends infinitely in all directions. But dark energy, particularly in the form of a cosmological constant, fundamentally changes that relationship. It doesn't clump together like matter, and it doesn't dilute as the universe expands. Instead, it acts as a constant outward pressure, stretching space and accelerating time's passage from one cosmic epoch to the next. Observations of the cosmic microwave background, large-scale galaxy clustering, and gravitational lensing patterns all suggest that the universe is remarkably flat on large scales, precisely what you'd expect in a universe delicately balanced between matter and dark energy, but it's a precarious balance. Slight changes in the amount or behavior of dark energy would tip the geometry, dramatically altering how light travels, how structures grow, and how the universe ultimately unfolds. This expansion isn't just a gentle swelling, it's fundamentally rewriting the ultimate destiny of the cosmos. If dark energy is truly constant, as the cosmological constant predicts, then galaxies will drift ever farther apart, stars will eventually burn out, and the universe will grow colder and emptier with each passing eon, a future often referred to as the Big Freeze. But if dark energy strengthens over time, as in some phantom energy models, it could lead to a big rip, a scenario where the expansion becomes so extreme that even atoms are torn apart and the very fabric of space-time is shredded. Alternatively, if dark energy decays or reverses its effect, the cosmos could eventually collapse in a big crunch, ending in a singularity of infinite density and temperature. The shape of tomorrow hinges entirely on the underlying physics of dark energy, and right now we are only guessing. To close the gap between theory and reality, physicists and astronomers have turned to a new generation of advanced instruments and ambitious sky surveys. The European Space Agency's Euclid Space Telescope is currently engaged in a groundbreaking endeavor, mapping billions of galaxies across the cosmos. This ambitious undertaking aims to chart the expansion history of the universe with unprecedented accuracy and to precisely measure the influence of dark energy as it unfolds across cosmic time. Simultaneously, the Vera C. Rubin Observatory in Chile is poised to commence its 10-year Legacy Survey of Space and Time, LSST, a project that will systematically observe the entire visible sky every few nights. This relentless scanning will generate an unprecedented dataset of transient celestial events, from supernova to near-Earth asteroids, and will also meticulously map the subtle distortions caused by gravitational lensing effects. Complementing these endeavors is NASA's forthcoming Nancy Grace Roman Space Telescope, a mission specifically designed to employ wide-field infrared imaging to detect the faint signatures of cosmic acceleration. By observing the universe in infrared light, the Roman Space Telescope will peer through cosmic dust, revealing distant galaxies and their subtle movements. Each of these missions is not merely intended to confirm the existence of dark energy. Instead, they seek to precisely constrain its properties. Scientists are eager to determine whether dark energy behaves like a cosmological constant, a uniform energy density permeating space, or something far more complex and dynamic. These experiments hold the potential to reveal whether dark energy evolves over time, whether it clumps together in unexpected ways, or even whether it connects to deeper yet-to-be uncovered layers of particle physics and field theory. However, despite these monumental efforts, fundamental questions about dark energy remain tantalizingly unanswered. What is its true nature? Why did it only recently begin to dominate the universe's expansion? Is it linked to quantum fields, the elusive vacuum energy, or something stranger altogether? Does it offer clues to the existence of extra dimensions, multiverse models, or undiscovered symmetries within the laws of physics? Could it even be a sign that general relativity itself, our very understanding of space-time, needs revision? In many ways, dark energy is more than just a phenomenon. It's a boundary, a vast and expanding edge to our comprehension. We know it exists. We perceive its influence in the movement of galaxies and the dimming of distant supernova. Yet its cause, its meaning, and its place in the grand puzzle of the cosmos remain hidden from our view. Black holes, those enigmatic cosmic entities, represent some of the most mysterious and extreme objects in the universe. They are born from the relentless force of gravity pushed to its ultimate limit. When a massive star exhausts its nuclear fuel, there is nothing left to counteract the relentless inward pull of its own weight. If this collapse is complete and unimpeded, the core compresses beyond all known states of matter, eventually forming a singularity, a point of infinite density where the very fabric of space-time breaks down. Surrounding this singularity is the event horizon, a boundary from which nothing, not even light, can escape the black hole's gravitational grasp. It isn't a physical surface, but rather a threshold. Once crossed, return becomes an impossibility. At the very heart of a black hole, our cherished laws of physics begin to falter. General relativity, the theory that describes gravity as the curvature of space-time, accurately predicts the formation of the singularity. However, it also signals its own limitations there. Infinite density, infinite curvature. These are telltale signs that a more fundamental theory is desperately needed. Quantum mechanics, which governs the behavior of particles at the smallest scales, offers no clear explanation for what transpires at the center of a black hole. The event horizon effectively shields that mystery from our view, locking it behind a veil that no signal can penetrate. We are certain that black holes exist, but we remain deeply uncertain about what lies within. For decades, the prevailing view was that black holes were relatively simple objects, completely defined by their mass, charge, and spin. They could voraciously swallow stars, gas, and even light itself. Yet they seemingly gave nothing back, leaving behind only a dark gravitational footprint. Then, in the 1970s, Stephen Hawking revolutionized our understanding. By combining concepts from quantum field theory and general relativity, He demonstrated that black holes are not entirely black. Instead, they emit a faint but detectable glow of particles, now famously known as Hawking radiation. This radiation arises from quantum fluctuations near the event horizon, where pairs of virtual particles spontaneously pop into existence. One of these particles falls into the black hole while the other escapes. From a distant vantage point, it appears as though the black hole is slowly evaporating. This was a truly revolutionary insight, but it also led to a profound paradox. As the black hole emits Hawking radiation, it gradually loses mass. Over vast stretches of time, if no new matter falls in, the black hole shrinks in size. Eventually, it might evaporate entirely, vanishing in a final burst of radiation. But here's the crux of the paradox. What happens to the information about everything the black hole once consumed? In quantum mechanics, a cornerstone principle dictates that information can never truly be lost. The evolution of a closed system is always reversible. The wave function, which describes the state of a quantum system, evolves smoothly according to the Schrödinger equation. However, in Hawking's picture, the radiation emitted is completely thermal, meaning it carries no imprint whatsoever of the black hole's internal contents. If the black hole disappears entirely and the information is not somehow encoded within the radiation, then it is lost forever. This blatant violation of one of the core tenets of quantum theory sparked what has become one of the most profound puzzles in theoretical physics, the black hole information paradox. How can we possibly reconcile Hawking radiation, which seems to suggest that information is destroyed, with a universe that, at its most fundamental level, is thought to conserve it? The stakes are incredibly high. If information can indeed be lost within black holes, then quantum mechanics itself may be incomplete. Conversely, if information must be conserved, then something fundamental about our understanding of black holes or even space-time itself must undergo a radical transformation, and the paradox only intensifies the closer we examine it. One of the most unexpected developments in black hole physics was the realization that black holes possess entropy. In classical physics, entropy is a measure of disorder, or more precisely, the number of microscopic configurations that can correspond to a given macroscopic state. A simple glass of water has entropy. A star possesses entropy. However, a black hole, seemingly defined only by its mass, spin, and charge, appeared far too simple to have significant entropy. It seemingly lacked the internal degrees of freedom that typically give rise to entropy. And yet Hawking's work, along with the contributions of Jacob Bekenstein, revealed that black holes must indeed have entropy, and that this entropy is proportional to the surface area of their event horizon rather than their volume. This represented a profound shift in our understanding. It suggested that the information content of a black hole scales with its boundary, not with what is contained within. Bekenstein's formula, later refined by Hawking, demonstrates that the entropy of a black hole is proportional to the area of the event horizon divided by the Planck length squared. This implies that the entropy of a black hole is immense, far exceeding that of ordinary matter with the same mass. This connection between area and entropy led to the development of the holographic principle, the mind-bending idea that the fundamental description of a region of space might be entirely encoded on its boundary, much like a hologram. However, understanding exactly what those microstates are and how they manage to store information necessitates a complete theory of quantum gravity. General relativity describes black holes as smooth, geometrical objects, while quantum mechanics demands a granular, probabilistic structure at the smallest scales. Reconciling these two seemingly disparate views necessitates a deeper framework, one that can accurately describe space, time, and information at the smallest possible scales. Several approaches have been proposed to bridge this conceptual gap. String theory, black holes can be modeled using collections of strings and branes whose quantum configurations precisely match the expected entropy. Loop quantum gravity, another leading candidate theory, describes space-time as a network of discrete loops, which might account for black hole microstates in a fundamentally different way. However, to date, no single theory has emerged as definitively correct, and the information paradox remains a persistent challenge. Proposed resolution suggests that the information is somehow encoded within the Hawking radiation after all, implying that the radiation is not truly thermal but rather subtly entangled with the interior of the black hole. As the black hole evaporates, quantum correlations might allow the information to escape in a scrambled but ultimately recoverable form. This would preserve unitarity, the fundamental rule that quantum evolution is reversible, and would safeguard the foundations of quantum theory. However, this resolution raises new and equally perplexing questions. How exactly does the information escape? Through what specific mechanism? And if it escapes, does that violate the fundamental principle that nothing can travel faster than light? To address this, some physicists have proposed a rather dramatic possibility, the firewall hypothesis. According to this controversial idea, the smooth horizon of a black hole is merely an illusion. Instead, an infalling observer would encounter a wall of extremely high-energy radiation, a firewall at the horizon, where quantum entanglement breaks down. This would allow information to escape, but at the cost of violating another cherished principle of physics, the equivalence principle, which states that freefall through empty space should feel smooth and uneventful. The firewall proposal preserves unitarity, but only by sacrificing one of general relativity's core symmetries. It's a bold and rather unsettling move, and one that remains highly controversial within the physics community. Some researchers view firewalls as a clear sign that we've reached the very limits of our current theoretical framework. Others consider them to be an artifact of overly strict assumptions. However, all agree that the ultimate resolution to the black hole information paradox will likely require entirely new physics, and perhaps even a complete reevaluation of what space, time, and information truly are. Despite their inherent mystery, or perhaps precisely because of it, black holes have become invaluable tools for physicists. They are far more than just astrophysical curiosities. They are crucibles in which the known laws of nature are pushed to their absolute breaking point. In the intense gravitational field near a black hole's event horizon, time slows down dramatically. Space stretches. Tidal forces grow so powerful that they can rip apart individual atoms. These represent the most extreme conditions that the universe naturally provides, conditions that simply cannot be replicated in any laboratory here on Earth. Studying black holes allows us to test general relativity in its most extreme regimes and to probe the very edge of quantum physics, where our current understanding begins to crumble. In that sense, every black hole acts as a natural experiment, a cosmic laboratory in which space and time are distorted beyond all ordinary recognition. We may not be able to directly peer into the singularity itself, but we can meticulously observe the behavior of matter and light in the immediate vicinity of the event horizon. We can precisely measure the orbits of stars around black holes, as has been successfully done at the center of our own Milky Way galaxy, where a supermassive black hole called Sagittarius A anchors our galactic structure. We can carefully study the accretion disks of superheated gas swirling around black holes emitting powerful X-rays and high-energy radiation. And now, with the advent of gravitational wave astronomy, we can directly detect the subtle ripples in space-time caused by the collisions and mergers of black holes, signals that carry information directly from the most violent events in the universe. These observations provide critical data points, but the deeper conflict stubbornly persists. Black holes reside at the intersection of two great yet fundamentally incompatible theories. Quantum mechanics accurately describes the probabilistic behavior of particles and fields at the smallest scales. It has been tested with extraordinary precision and has repeatedly proven its predictive power. General relativity, on the other hand, describes gravity as the curvature of spacetime, and it has flawlessly passed every observational test in the macroscopic world. However, when we attempt to combine these two theories, particularly in extreme environments such as black holes, serious contradictions inevitably arise. The information paradox is but one example. Singularities are another, and the inherent inability to describe what is happening inside a black hole clearly demonstrates that neither theory, on its own, is complete. This fundamental incompatibility has driven the relentless search for a comprehensive theory of quantum gravity, a unified framework that can accurately describe all forces, all particles, and all scales within the universe. String theory and loop quantum gravity are currently the leading contenders, but both remain mathematically complex and extraordinarily difficult to test experimentally. Holography, which is inspired by black hole entropy, offers another promising path. According to the ADS/CFT correspondence, a profound duality proposed within string theory, a gravitational theory in a higher dimensional space can be entirely equivalent to a quantum field theory without gravity on its tame boundary. In this theoretical picture, a black hole in one universe corresponds to a quantum system in another where information is perfectly preserved. This holographic principle has quickly become a powerful tool for studying quantum gravity in highly symmetric spacetimes. Even if this specific duality doesn't directly apply to our universe, it strongly suggests that space and time may be emergent, not fundamental, ingredients of reality, but rather macroscopic effects that arise from far deeper quantum structures. Such a revolutionary view, black holes might not be puzzles contained within space-time, but rather crucial clues as to how space-time itself comes into being. And so, black holes continue to illuminate the deepest fault lines in modern physics. They demand that we confront the paradoxes that we might otherwise prefer to ignore. They blur the lines between the known and the unknown, between the classical and the quantum. And the so in this it's an else from these two what all they are whether at the very quantum but when they simply not a without a it remain in this one of the string in order for these others in this loop both theories, string theory and loop quantum gravity, are undeniably powerful, elegant, and deeply speculative. Neither has yet been confirmed by any direct experimental evidence, which offers a tantalizing glimpse of what a complete theory of quantum gravity might ultimately look like. But both share a common overarching goal: to understand how the smooth fabric of space-time emerges from something far deeper, something inherently granular and undeniably strange. At the heart of quantum gravity lies a truly fundamental question. Is space continuous, or is it instead composed of discrete units? In general relativity, space and time form a smooth, continuous fabric, a seamless backdrop against which all cosmic events unfold. However, quantum mechanics strongly suggests that at incredibly small scales, this perceived smoothness must inevitably break down. The Planck length, approximately 1 to 6 × 10⁻35 meters, is widely thought to be the smallest meaningful unit of distance. Below this scale, quantum fluctuations in geometry become so intense that space itself effectively loses its classical meaning. Distances blur, and the very notion of where begins to dissolve into a probabilistic haze. Time, too, may not flow smoothly and continuously, but may instead emerge from more fundamental quantum processes. This leads to a radically different picture of reality, one in which space and time are not fundamental constituents but rather emergent properties. In some theoretical models, space-time is composed of tiny units, quanta of geometry, much like matter is composed of atoms. In loop quantum gravity, these fundamental units take the form of spin networks, which define areas and volumes with discrete spectra. String theory, the granular structure emerges from the vibrations and interactions of strings and branes. In causal set theory, spacetime is modeled as a series of discrete events connected by causal relationships. In all of these scenarios, the smooth continuum of general relativity is merely an approximation, a large-scale limit of something far more fundamental and undeniably quantum. However, probing these ideas experimentally is extraordinarily difficult, if not entirely impossible, with current technology. The Planck scale is so far beyond the reach of today's particle accelerators that direct tests are effectively unattainable. Even the Large Hadron Collider, LHC, the most powerful particle accelerator ever built, operates at energies more than 1 trillion times too low to directly probe quantum gravity effects. But physicists are nothing if not resourceful, and they have grown increasingly creative in their search for indirect clues. For example, a theory of quantum gravity might subtly violate Lorentz invariance, the fundamental principle that the laws of physics are the same for all observers, regardless of their relative motion. These tiny violations could potentially leave faint imprints in high-energy cosmic rays or in the polarization of light emitted from distant gamma-ray bursts. Another potential window into the quantum realm is the cosmic microwave background, CMB, the afterglow of the Big Bang. The early universe was so dense and hot that quantum gravity effects might have left subtle fingerprints in its fluctuations. Patterns in the polarization, non-Gaussianities, or unexpected correlations within the CMB might offer valuable clues. Similarly, gravitational waves, especially those originating from the very early universe, could carry signatures of the underlying quantum structure of space-time. Though detecting them with sufficient sensitivity remains a daunting technological challenge, some researchers are also studying black holes for experimental insight, hoping to detect echoes and gravitational wave signals from merging black holes, tiny deviations from classical predictions that might hint at quantum corrections near the event horizon. Still, the vast majority of evidence remains theoretical, deeply mathematical, and as yet unobservable. This hasn't deterred physicists in the slightest. Quantum gravity is not solely about building bigger and more powerful machines. It's fundamentally about building coherent conceptual frameworks that push the very limits of logical consistency. Even without direct experimental confirmation, theoretical tools such as holography, dualities, and renormalization have significantly deepened our understanding of quantum fields, thermodynamics, and the very nature of space-time itself. Doing so, they help to illuminate the contours of a theory that we have not yet fully completed, but one that we remain steadfastly convinced must exist. And when that elusive theory is finally discovered, it will not just unify the fundamental forces of nature, it may fundamentally reshape our understanding of what the universe truly is. Everywhere we look in the universe, we see matter, galaxies, stars, planets, dust, gas, all composed of atoms. And atoms, in turn, are composed of protons, neutrons, and electrons, the fundamental particles of matter. But here's a profound puzzle. According to our best theories of the early universe, matter simply shouldn't exist in this abundance. In fact, it shouldn't exist at all. When energy condenses into particles, it should create matter and antimatter in perfectly equal quantities. A proton and an antiproton, an electron and a positron, existing side by side in perfect symmetry. But if that had indeed happened perfectly, those particles would have relentlessly annihilated each other, leaving behind only radiation. No galaxies, no stars, no atoms, no planets, no people. Somehow, in the earliest moments of the universe, a subtle imbalance occurred, a tiny excess of matter over antimatter. For every billion pairs of matter and antimatter particles created, there was one extra particle of matter. That seemingly insignificant difference was enough to change the entire fate of the cosmos. The vast majority of particles annihilated into light, but the tiny amount of leftover matter ultimately formed everything that we see today. This crucial process, the origin of the asymmetry between matter and antimatter, is known as baryogenesis, and it remains one of the most profound and unsolved questions in modern physics. Why was there more matter than antimatter? What fundamental processes broke the symmetry and allowed matter to ultimately dominate? The search for answers begins with CP violation, a subtle breakdown in the symmetries of nature. In physics, the combination of charge conjugation, C, and parity transformation, P, describes how particles behave when they are flipped into their mirror image opposites and exchanged with their antiparticles. If the laws of physics were perfectly symmetric, CP would hold, meaning that matter and antimatter would behave identically under mirror reflection and charge reversal. But experiments have convincingly demonstrated that this isn't quite true. In certain decays of subatomic particles, such as kaons and B mesons, the probabilities differ ever so slightly for matter and antimatter. This violation of CP symmetry is one of the few known ingredients that are potentially capable of generating a matter-dominated universe. However, the amount of CP violation that has been observed so far is far too small to account for the vast matter-antimatter imbalance that we see today. The standard model of particle physics acknowledges CP violation, but it's woefully insufficient to account for the observed matter-antimatter asymmetry. This discrepancy strongly implies the existence of new physics, processes or particles beyond the standard model that could have generated more substantial asymmetries in the early universe. One prominent theory attempting to explain this is electroweak baryogenesis. This hypothesis posits that during the electroweak phase transition, when the electromagnetic and weak nuclear forces decoupled, certain interactions preferentially favored the creation of matter. Such interactions would necessitate the existence of novel particles and forces potentially within reach of detection at high-energy colliders like the Large Hadron Collider, LHC. Imagine a scenario where the universe, in its infancy, was a seething cauldron of energy. As it cooled, these new particles, influenced by new forces, tipped the scales ever so slightly toward matter, laying the foundation for everything we see today. Another compelling possibility arises from leptogenesis, a theory that shifts the origin of the asymmetry from baryons, protons and neutrons, to leptons, electrons, muons, and neutrinos. In this scenario, hypothetical heavy right-handed neutrinos, particles conspicuously absent from the standard model, decay in a manner that violates CP symmetry, resulting in a surplus of leptons over antileptons. These lepton asymmetries are then converted into baryon asymmetries through interactions predicted by the standard model, albeit occurring at extraordinarily high energies, far beyond our current experimental capabilities. Leptogenesis is particularly appealing because it also offers a potential explanation for the remarkably small masses of ordinary neutrinos, a long-standing puzzle in particle physics. It's as if these heavy neutrinos are ghosts, influencing the universe from beyond the veil of the standard model. Both electroweak baryogenesis and leptogenesis offer promising theoretical frameworks, but definitive experimental confirmation remains elusive. They hinge on physics that we have not yet directly observed, new particles, new interactions, new energy scales, and so the mystery persists. Why, in a universe that should have produced equal amounts of matter and antimatter, are we here at all? To unravel the origins of this profound asymmetry, scientists have turned to some of the most sophisticated and precise instruments ever conceived, particle accelerators. At facilities such as the Large Hadron Collider, LHC, at CERN and Japan's Super KEKB accelerator, researchers meticulously study rare particle decays. A particular focus lies on B mesons, short-lived particles containing a bottom quark. These particles exhibit CP-violating behavior, offering a window into the subtle differences between matter and antimatter. By carefully comparing the decay patterns of B mesons and their antiparticles, physicists can measure the minute discrepancies that hint at the underlying symmetry breaking. These measurements serve as stringent tests of the standard model and searches for deviations that might point to new, undiscovered physics. So far, the results have confirmed the presence of CP violation, but as before, the magnitude observed remains insufficient to account for the cosmic imbalance. Still, these experiments play a crucial role in narrowing the search. They constrain the properties of potential new particles and interactions that might exist at higher energies or within hidden sectors of the universe. Some theories suggest that heavier versions of the Higgs boson, or as yet undiscovered particles related to supersymmetry, could amplify CP violation during the phase transitions in the early universe. Their models predict that the asymmetry might be intricately linked to new forces that couple differently to matter and antimatter, leaving subtle yet detectable traces in decay channels or mass differences that future colliders could potentially uncover. It's a painstaking process, sifting through vast amounts of data, searching for the faintest whispers of new physics. Beyond the realm of particle accelerators, scientists are also exploring the fundamental symmetries of nature itself, seeking violations of the most basic assumptions about particles and their mirror image counterparts. One particularly compelling approach involves searching for the electric dipole moment, EDM, of fundamental particles, such as the neutron or electron. If these particles possess an intrinsic asymmetry in their charge distribution, a lopsidedness, so to speak, it would unequivocally signal a violation of time reversal symmetry and, by extension, CP symmetry. Experiments employing ultra-cold neutrons and precision atomic clocks have pushed the limits of EDM detection to astonishing levels of precision. To date, no non-zero EDM has been observed, but the constraints continue to tighten, effectively ruling out broad classes of theoretical models. Each null result, while not providing a direct discovery, chips away at the landscape of possibilities, guiding theorists toward more viable explanations. Meanwhile, theorists continue to delve into the conditions that might have prevailed in the earliest moments of time, mere fractions of a second after the Big Bang. In that primordial epoch, the universe was an incredibly dense and hot plasma of quarks, gluons, leptons, and radiation. Temperatures and energies were far beyond anything we can currently recreate in a laboratory. But within that chaotic environment, even small imbalances could have had profound and lasting consequences. Some models suggest that the asymmetry arose through spontaneous symmetry breaking, a type of phase transition akin to water freezing into ice. In this scenario, different regions of the universe could have settled into slightly different states. If those states favored matter in some regions and antimatter in others, the resulting dynamics could have left behind a cosmos dominated by matter. In such scenarios, topological defects such as domain walls or cosmic strings might have formed. These exotic structures in space-time represent regions where symmetry breaking was incomplete or varied. They could have acted as catalysts for baryogenesis, concentrating CP-violating processes and amplifying their effects. While there is currently no direct evidence for such defects, they remain an intriguing possibility, one that seamlessly connects high-energy particle physics with the large-scale evolution of the cosmos. They are theoretical bookmarks, reminding us that the universe's secrets might be hidden in the fabric of space-time itself. Alternatively, other mechanisms invoke interactions with inflaton fields, the hypothetical energy fields that drove the period of rapid expansion known as inflation, or draw inspiration from ideas originating in string theory and extra dimensions. Each of these proposals offers a distinct pathway to the same destination, a universe predominantly composed of matter. And while none has yet been definitively proven, they serve as a constant reminder that the origin of matter remains a complex and unsolved problem. It's a scientific frontier where theory and experiment are engaged in a constant dance and where the most fundamental questions of existence remain tantalizingly open. The pursuit of understanding this asymmetry is not merely an academic exercise. It's a quest to understand our place in the universe. The consequences of the matter-antimatter asymmetry are imprinted across the entire structure of the universe. The very fact that a tiny excess of matter survived the primordial annihilation is why the cosmos was left with enough material to form hydrogen and helium during Big Bang nucleosynthesis. These light elements then seeded the first stars, which through nuclear fusion and supernova explosions forged the heavier atoms that constitute planets, molecules, and life itself. The very existence of galaxies, from the smallest dwarf spheroidals to the largest massive spirals, hinges on that 1 in a billion imbalance that was established in the universe's earliest moments. If the symmetry had been perfect, the universe would have ended up as a sea of photons, hot, dense, and utterly sterile. The cosmic microwave background, CMB radiation, the afterglow of the Big Bang, still bears the faint imprint of this ancient violence. It exhibits a nearly perfect blackbody spectrum, but with subtle fluctuations, ripples in temperature and density that eventually grew into the galaxies and clusters we observe today. These fluctuations reflect the behavior of matter in the early universe, and their very existence implies that some matter survived while antimatter did not. Even today, the distribution of matter is uneven, while the antimatter component is essentially absent. Searches for large regions of antimatter, anti-galaxies, anti-stars, or anti-planets have yielded no compelling evidence. If such structures existed, we would expect to see intense gamma-ray signatures resulting from the annihilation of matter and antimatter at their interfaces, but the sky remains largely quiet. Antimatter is produced in small quantities in high-energy processes, such as cosmic ray interactions or particle accelerator experiments. But these are transient events, not indicative of large-scale antimatter worlds. The visible universe appears to be composed almost entirely of matter, and yet despite all its observable consequences, the origin of the asymmetry remains stubbornly elusive. None of the known mechanisms within the standard model of particle physics can adequately explain the magnitude of the imbalance. The CP violation observed in meson decays is real and measurable, but its effect is simply too weak. Furthermore, the standard model lacks heavy neutrinos, an extended Higgs sector, and a sufficiently strong phase transition required to drive efficient baryogenesis. This shortfall represents one of the strongest arguments for the existence of physics beyond the standard model, a clear indication that what we currently consider to be complete is, in fact, missing critical pieces of the puzzle. I hope you sleep well and dream softly. Good night. Music. 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 Heat. Heat. Music. 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 Cue. Music. 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 Cue. Music. music, 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 music. Heat, music, 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 heat, heat, music, 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 music. There you go. Music, 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 heat, heat, music. I whispered, I hope you sleep well and dream softly. Good night. The lullaby began, a gentle cascade of notes that filled the small, dimly lit room. Music, 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 music. The music swelled, then softened again, washing over me like a warm tide. Heat, heat, the sensation pulsed through my veins, a subtle yet insistent reminder of the process, of the change occurring deep within. Music, 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 music. The melody continued its soothing rhythm, a counterpoint to the rising thermal energy. Thank you, murmured, barely audible, a small offering of gratitude for the unseen hands guiding me through this transition. Music, 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 music. The music grew a little louder, as if acknowledging my thanks. Thank you, music. I repeated, feeling a strange lightness, a sense of shedding something heavy. Thank you. Music, 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 music. The music enveloped me completely, a comforting blanket against the encroaching unknown. Heat, heat. The burning intensified, not painful but undeniably present, like a forge burning at my core. Music, 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 music. The notes seemed to vibrate in harmony with the increasing heat. Heat, heat, music, 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 music. A wave of relief washed over me, a sign that the process was nearing completion. There you go. Music, 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 music. The music faded slightly as if taking a breath. Heat, heat. The sensations settled. A warm glow rather than an intense burn. Music.